we're on. Now, so this is 56. This is 56. This is 57. Okay? That's 57. And what's lutetium? Over here, what's lutetium?
71.
71. This is 71. And then this is 72, 73. And what number is this here? What number is that?
87.
What is it?
Which one? The lower left corner?
Yeah, the francium. Yeah.
87.
87, right? This is 87. 88, right? This is 89, right? What's this down here? You're close to the table. 103. Okay, that's important. So this will be 104, 105, etc. Clear? You get it? That's important. So you want to number this. Okay? This is going to be for homework, by the way. So I want this on the next class day. I want at least to where we are. Now, what column up there is extraordinarily, extremely, unbelievably, without a doubt, when you think stable, it's really stable?
The last column.
The last column on the right. So this column here.
Noble gases, right?
Yeah, what did you say? What did you call them?
Noble gases.
The noble gases. So there's a lot that you know about the periodic table, isn't there? Yeah, noble gases. Yes, the noble gases. And they're very stable, right? Now, here I have two objects. We can say that they're atoms if you like, but two objects. Okay, two atoms. A red one and a black one. Okay? Are you done? Everything's all right? Excellent. So, let's just pretend I'm bonding them, connecting them, okay? What part of the atoms are going to touch first? Yes?
The electrons.
It's a little too specific. Yes? The outside. The outside, right? The outside of the atoms, correct? Yeah. I'm telling you, you guys know a lot. Why are you even in here? Why are you taking chemistry? You took chemistry. Okay. No, you thought you took chemistry. So, the outer electrons. Somebody over here said the valence electrons, and that's correct. What are the valence electrons? They're the outer shell, the outer electrons. You're doing all right. Very impressive. Okay? Now, all right. Good. Now, if that's true, then what would you say about the valence shell of these atoms? Kaylee? It's full. I don't know if I want to say the word full yet.
They have 8 electrons.
Well, that's not. I don't want to use the word 8. I don't want to use the number 8. I don't like the octet rule. Octet rule is for people that, don't have a lot on the ball. They're stable, right? There's something about the valence shell that's stable. There's something about, because when an atom combines, they're really combining the outer, right? The outer electrons, right? So there's something about the outer electrons here that are very. They don't need to gain or lose. Okay, so there's a lot of things that you guys already know, but this is my point. This is my point. I don't use the octet rule. I don't say that. What I say is that all of these atoms are trying to be like these atoms. There's something about the structure of the noble gas, and that's what's going on. Yeah, you could look after the fact and say, well, they're all seeking 8, etc. Well, lithium. Is that going to seek 8? Yes.
That's why the first equation +1 +2 +3.
Well, so is that going to have 8?
It's going to be +1, so it loses 1, so
It'll be what?
it'll be 0.
No, it won't be 0.
It's 1, but
No, absolutely not. What's its new valence shell? If lithium gives up 1 electron,
2.
what's its new valence shell?
2.
Well, right, but what's it like? What does it look like? It looks like the valence shell of what?
Helium.
Helium. Yeah. It's imitating the valence shell of helium. Helium doesn't have 8.
It's 2.
If aluminum gives up 3 electrons, where's aluminum? Right here? Right? If aluminum gives up 3 electrons, right?
Under.
As boron, where's aluminum?
Under.
Under it. Well, isn't it similar to boron?
Yeah.
Because they're both going to give up 3 electrons. That's the same is going to be for these atoms, right? Aren't they 3 away from being like the nearest noble gas? Are they going to give up 3, or are they going to take on 5? What do you think is easier?
Give up 3.
Yeah, because everything seeks to do it the easy way.
That's what I was asking.
Excuse me?
That's what I was asking.
When what was there? I didn't hear a question.
My first 3, the first column, second column, the one on the E block.
Mm-hmm.
First one +1 and +2 +3, they lose 1, 2, 3.
Yeah, and that's correct. They do. I mean, in terms of odds, there are certainly exceptions. Not exceptions, but there are physical properties or physical changes or physical things that will prevent something from behaving in terms of percentages. But my point is that boron, if it gives up 3, it's going to be like helium, right? But if aluminum gives up 3, it's going to be like what? If aluminum gives up 3, it'll be like what?
Neon.
It'll be like neon, right? So aluminum gives up 3, it has 8. Boron gives up 3, it has 2. I mean, do you know how many, so how many atoms, you don't have to give me a number, just say a lot. How many atoms, when they become ions, are going to have 2 electrons in their valence shell? A lot. Right? They are. You have lithium, beryllium, right? They're going to gain, they're going to lose, right? So you have, 3 is a lot. You can make all kinds of chemicals with that. Because what can you do? You know you can make lithium chloride, lithium bromide, lithium iodide, right? And you're coming up with particles where one of the elements has not 8 but 2 electrons. So I don't use the octet. I don't say that. You'll never hear me say the octet ever. What I say is that the atoms. Let me ask you a quick question. What's the relationship between the number of protons and the number of electrons in an atom? What's the relationship between the number of protons and the number of electrons in an atom? They're equal. They're equal. They're equal. Just keep it simple. They're equal. Right? The ion, when it reacts and gets a charge, then it's not going to be equal, correct? Yes? Now, let me just review, and you already know this, right? So, what are all of these elements going to do? What are all of these elements going to do when they react? They're all going to give up 1 electron, right?
Yep.
So they're all going to be +1. These are all going to be +2. These are all going to be +3. These will be +4, -4, depending on whether or not they want to give up or take on 3 electrons. These are all going to be -1 because they're all going to take on an electron, right? So it's all charges. So I don't do the octet rule. I do the noble gas configuration. That's what they're shooting for. Are we done, or don't we have 3 minutes?
4 minutes.
We have like 4 minutes? Okay. So those are the charges, and that's the way we do the charges. Okay, now. I only have 4 minutes. I'm chafing at the bit. I have a lot to do, a lot to talk about. Because when I talk on, what's the next day? Monday. We're going to talk about electron configurations, how things are filled. We're going to talk about the electron distribution. And then when I talk about the electron distribution, and we kind of figure out that the volume of the atom is mostly what? Is mostly what? The volume of the atom is mostly what? Nothing. It's mostly nothing. Does an electron have a mass? Not really. Well, it has a mass, but it's like 1 over 1,840. So then I'm going to talk about what? What do you think I'm going to talk about at that point from chapter 4? When we establish that the volume of the atom, because I can't teach this as if you don't know something about chemistry. So what am I going to talk about briefly? It'll take 5 minutes. What am I going to talk about when we establish that the atom is mostly empty space? The gold foil experiment. Yeah, that was the whole idea. The vast majority of the deflections of the alpha particles. What's an alpha particle? Lula? What's an alpha particle? Don't know? Okay. Has anybody read chapter 4?
Wasn't it the one they shot it at the gold foil?
Right, but an alpha particle is just a helium atom without the electrons. It's a helium nucleus. So as I shoot these alpha particles at the gold foil, less than 5%. Not less than 5%. The vast majority of them, like 98%, some enormous number, were deflected 5 degrees or less. It's amazing, really. So what can you say, therefore, about the nucleus? It's really small and it's really dense. What is a black hole? Does anybody know what a black hole is? What they theorize a black hole is made of? Anybody will? Compressed stuff, but what is it? What do they? If you take a sun and you take out all of the electrons and you just keep the nuclear material, that's kind of like a black hole. If you took the entire Earth and took out all the electrons and just took the nuclear material, it would be very small. It would have this enormous density. If you took the mass of the Earth in just nuclear material, you couldn't pick up a thimble full of it. You couldn't do it. So what the gold foil experiment showed you was that A, the nucleus is very small, but it's extremely dense. And it's the relationship between that nucleus and the electrons that we have to look at. Clear? Yes?
Black hole have a shape.
Excuse me?
Black hole have a shape.
I don't know. You know what? I don't know a lot about black holes. Is it kind of like an amoeba where it kind of wiggles around? I don't know, really. Does it have a defined shape? I know people can see them. You know what? I don't know a lot about black holes. I don't know a lot. So we've got to get out of here, okay? All right. See you on Monday. Have a great weekend. Be careful, please.
And we call water hydrogen oxide.
Not hydrogen.